We're going to do Chapter 11, Review for the Test. Question number 1. In the diagram below, a train of waves is moving along a string. What is the wavelength? Okay, so the wavelength is the distance from crest to crest or trough to trough. That's what a wavelength is. The wavelength is from here to here or here to here. But they don't show that in the diagram, so we can figure it out. So what we're going to do is first we have to count how many waves we have. So I'm actually, from where a wave starts to the next successive same part in the next wave, that's one wave. So I'm going to count the waves. I have 1, 2, 3 waves. So I have 3 waves. Now they made it easy for you. You know why? See how they put these vertical lines? So you could actually see 1, 2, 3. If they don't do those vertical lines, do them yourself. Okay? So there's 3 waves, and then the distance is going to be 6 meters. So if there's 3 waves and there's 6 meters, that means one wave is going to be 2 meters, which is B. Number 2, what is the amplitude of the wave represented in the diagram? So I'm looking at my picture. What's the definition of amplitude? Well, in waves, and in physics, we always have to have a frame of reference. So our frame of reference is the rest position. The amplitude is from the rest position to the crest, which is the top of the wave, or it's from the rest position to the trough, which is the bottom of the wave. If we look at here, they give us from crest to trough. So the amplitude is from the rest position, so it's 2 meters, but it's half of that, so the answer is 1 meter A. Now you notice that they give you information that you don't need. They give you this distance, which has totally nothing to do with the question. Number 3. It says when a transverse wave is moving through a medium, what is the action of the particles in the medium? So remember, we did a lab last week, transverse wave. So a transverse wave, if you looked at your lab, if you look at your notes, that's the one that looked like this. So as the wave is moving from left to right, the particles in the medium are moving perpendicular, and that is C. Again, when you're doing these problems, you should be looking for keywords. Transverse, and then we see here the keyword in all that verbiage is perpendicular. So the answer there is C. Number 4, as the longitudinal wave passes through a medium, the particles of the medium move. So the key word here is longitudinal. So we know in a longitudinal wave, we saw this in the notes, we did it in the lab last Friday. So the answer here is they move in the same direction, so that's going to be parallel. So the answer here is also C. Number 5, as the frequency of a wave increases, what happens to its period? So the first thing I'm going to say to myself, what is the relationship between frequency and period? Well, I know the reciprocals of one another. So it says as the frequency increases, what happens to the period? So the period T is equal to 1 over F. So as this gets bigger, as this increases, what happens to this? Well, that's going to decrease because they are inversely proportional, and you can tell just by looking at the equation. Number 6. A periodic wave with a frequency of 10 hertz would have a period of, so again, I'm going to be using the same equation. T is 1 over F, so it's equal to 1 over 10, which is just 0.1. So the answer there is B. I don't even need to use a calculator. Number 7. A wave has a frequency of 2 cycles per second and a velocity of 5 meters per second, the distance covered. So first of all, the choice isn't even here. There's a typo on here. Okay? But let's talk about how we're going to do this. Well, first they tell us the frequency is 2 cycles per second. They tell us the velocity is 5 meters per second. And they tell us the distance it covers it in 5 seconds. But they say, what is the distance covered? I don't need the frequency. I know that velocity is distance over time. So I can rearrange this equation, and I can say x is equal to v times t. So x is equal to 5 meters per second times 5 seconds. 5 times 5 is 25, and I see that this second in the denominator cancels with this second in the numerator, and I get the correct unit for distance, which is meters. So the answer is 25 meters, and I just changed that one. I don't know why, but it doesn't matter. But the answer is 25, and the choice was not there. Okay. All right, now we're going to look at number 8. So number 8 says, a wave is traveling at 5, so that's the velocity, so v is equal to 5.0 times 10 to the 4 meters per second. It has a wavelength, that's lambda, 2.5 times 10 to the 1 meters. What is the frequency? So I want to find f. So the equation that relates these three is v is equal to f lambda. So f is equal to v over lambda, so it's 5 times 10 to the 4 meters per second, divided by 2.5 times 10 to the 1 meters. So what happens here is that this meter cancels with that. My unit is 1 over a second, which is the correct unit for hertz. And then this divided by this numerically comes out to be choice B, 2 times 10 to the 3 hertz. Number 9, what is the velocity of a water wave that travels a distance of 10 meters in 5 seconds? So I have 10 meters, and then I have t is equal to 5 seconds, so v is equal to x over t. So 10 meters over 5 seconds, 10 divided by 5 is 2, and a meter divided by a second, which is a meter per second, which is the correct unit for velocity. So that's choice B. Number 10. The diagram below shows 2 pulses traveling in opposite directions through a transmitting medium. Which direction best represents the resulting pulse when the pulses combine? So when they combine, we learned about destructive and constructive interference. So when you think about the words in layman's terms, it's kind of like the same in physics, whereas constructive means they add together, and destructive means they cancel each other out. So if we look at the picture, these two are both on the top, so when they come together, they're going to add together, which is choice D. When we look at number 11, it says the diagram below shows 2 pulses of equal length traveling toward each other. Which diagram best represents the shape of the rope when the pulses are in region AB? So again, in physics, we always have a sign convention. We'll use the same sign convention here. We'll call it above positive. We'll call it below negative. So you see, this is like a positive 0.05. This is a negative 0.15. So when they add together, it's going to be negative 0.1, which is choice C. Okay, now we're going to do the back of the multiple choice. So flip your papers over. All right, so now on the back, number 1, if the spring constant of a spring is doubled, but the mass attached to it remains constant, then the period would be multiplied by. Okay, you don't do these in your head. You don't do pretend numbers. We're going to do it the correct way. The correct way is first you write the equation. So the equation for mass on a spring is T is equal to 2 pi times the square root of m over k. Then we take our equation and we do whatever they say to do with whatever is going to be changed. So that says I am going to double the spring constant. So here's my equation, T is equal to 2 pi times the square root of m over 2k. So when I compare the basic equation with the one with the spring constant, the only difference is there's a 2 down there. So the only difference is underneath the radical, in the denominator, there's a 2. But it's under a radical. So if I want to simplify this math-wise, what's the square root of 1? 1. So that's why it's 1 over radical 2, which is choice B. That is the way you do these problems. You don't guess. You don't do it in your head. You write down your equations, and you'll never get these wrong. And this is standard on math tests, science classes, everything. All standardized tests have questions like this. Number 2, a 10-kilogram mass supported on Earth by a spring oscillates with a period of 12 seconds. This mass spring system is now moved to the moon where gravity is 1/6. What's the new period? Well, the period for a mass on a spring, again, is 2 pi times the square root of m over k. Where is gravity in that equation? It's not there. Is gravity in that equation? So does gravity have anything to do with this? Is the mass changing when it goes to the moon? Is the spring changing? So the answer is going to be 12 because it doesn't change, so the period is going to be the same. If you're not sure, if you write down the equation and look at it, that would help you to visualize that. Number 3, a simple pendulum has a period of oscillation of approximately 2 seconds. When the length of the pendulum is doubled, what happens to the period? So the first thing I'm going to do is I'm going to write down the period of a pendulum as 2 pi times the square root of L over G. Then I'm going to say, well, what happens? I'm doubling the length. So when I say T is equal to 2 pi times 2L over G, the only difference here is there's going to be a radical 2 in the numerator. So I see if there's a radical 2 in the numerator, the difference is whatever the period is, it's going to be multiplied times radical 2, because that's the only difference. So then I take my calculator, and I say the square root of 2, which is 1.4, and then I multiply it by 2, and it comes out to be 2.8. So I say radical 2, and then I multiply that times the 2 seconds for the period, which it was initially. So that's 2.8, which is E. Number 4. A simple pendulum has a period of 3 seconds on Earth. On the moon, where the acceleration due to gravity is approximately 1/6, its period be what? So the period of a pendulum, T is equal to 2 pi times the square root of L over G. So now on the moon, the period is 2 pi times the square root of L, but it's going to be G divided by 6. So now on the Earth, this period is 3 seconds. So now the difference here is everything is the same except I have this G here. Now, if you're not good with your algebra, you write it out. So remember, L divided by G divided by 6 is going to be the same as L times 6 over G. So underneath the radical, this is actually 2 pi times, it's actually 6L over G. So the difference is I have radical 6 in the numerator. So I multiply radical 6 times 3, and I get my answer, which is 7.3. This is the correct way to do these problems. Again, you don't put in pretend numbers, and you don't do anything else. Okay, that's the way you do these. Okay, the last one, number 5, it says a pendulum and a mass spring system each have a period T. If the mass of each system is halved, what happens to the new period? So first, let's talk with the pendulum. The period of a pendulum is equal to 2 pi times the square root of L over G. So now the mass is going to be half. Is mass even in this equation? No. So the period is going to be the same. So that means the period is going to be the same. Well, this one's different, and that one's different. So I already eliminated 3 choices. So when I do it, the period is going to be the same, which is going to be T. Now for the period of a mass on a spring, if T is equal to 2 pi times the square root of m over k, now if the mass is half, the new one's going to be T is equal to 2 pi times the square root of m over 2 times k. So algebraically, I just put that 2 there in the denominator, so it would be m over 2k. So it would be, the period would have a radical 2 in the denominator. So that's why here the period would be T divided by radical 2. And that would be the difference. And that would be choice D. And again, this is the way that we do these problems. First we write out the equation the way it appears. Then we do whatever they ask us to do, which is either multiply and divide whatever one of the values. And then we just compare them. And it's very simple. And then you don't get these wrong, because these are actually simple questions. Okay? And that's it.